way, you know, I did not upload because it's still on the way. So now, yesterday we were computing the feature information matrix entry. So we started to compute, you know, the feature on amplitude and frequency, which, by the way, is the one that I computed behind, so it's close to 0, and then, you know, this one is close to 0. I continue with yesterday. Then okay, so on the exam, on the exercise yesterday, I computed this one, A omega, and, you know, let me look at I omega omega, okay, for instance. On I omega omega, I simply take this part of the feature and I put together, so I make the square for that. So let me move it on a new page. So I omega omega, okay, which is equal to 2 times divided by n0 integral of minus, so this term, point.
Doesn't work.
Here. Because here, you know, I have I omega omega, and it is computed by the integral of 0t of this term to the square. So I have a squared, t squared, sine squared. Okay. So a squared, t squared, sine squared, omega 0 t plus phi dt. Now, so, you know, looking at this term, I have a sine square. The sine square is 1 and the plus cosine of 2 omega. Now the cosine of 2 omega, so, you know, so this one is equal to 2 times n0 a squared, and then I have integral of t squared, then it is divided by 2 plus cosine 2 omega 0 t plus 2 times phi multiplied by t squared divided by 2 in dt. Now, for the same reason before, this term is approximately equal to 0 because it's a parabola with a sinusoid inside. And so the integral of that one is all the positive and negative, and, you know, if the frequency is very high, all the positive cancel with the negative. So that one is approximately 0. So this is approximately equal to 2 times a squared divided by n0. Then I have a 1 over 2. Then I have an integral of t squared dt. Okay, which makes, so this goes away with that. So I have a squared divided by n0. And then it is t cubic divided by 3. Okay. Now, so, you know, I apply the same rule for all. Okay, so I don't want to, you know, I want to show you the most critical one. Then I apply this rule for all, and then I get the feature information matrix, which I already computed here. So the feature is here. So let me copy and paste. Okay, so by repeating many times, what I got is the feature here. Now, remember, you know, the ordering is that here I have the amplitude, here I have the omega, and here I have the phase, phi. So here what I notice again that, you know, the amplitude is decoupled by frequency and phase. Because, you know, you can read from here. It's because, I mean, it's the amplitude, there is all these zeros. So what I can conclude that looking at the Fisher information matrix, even for continuous time, the amplitude is decoupled from frequency and phase. Now, what I can do is assume that, you know, now I ask you, can we do something to decouple the signals? Now, going back, I can do something. Because, you know, going back, you know, I can decouple the cross terms. And the cross terms are here. So, which is I omega phi. So, if I manage to have I omega phi to be 0, then, you know, these are decoupled. So, let's see if I can do it. Now, going to the computation of I of all the entry, okay, and compute it to make it decoupled, then I need to revisit the extreme of integration. So all the extreme of integration, rather than being between 0 and t, they go between minus t divided by 2 and t divided by 2. So that means that what I'm doing is similar as I did before. So rather than considering the interval between 0 and capital T, or 0 and n if discrete time, I consider between minus capital T half and capital T half. Okay? So that means that, you know, in the second case, I have this signal, and, you know, I relabel or I measure it within the T interval. But, you know, this is minus T half, this is 0, and this is T half. Now, if my parameter of interest is a phase, then this trick cannot be done. If my parameter of interest is a frequency and phase is a nuisance, then it's something that I can do. Why phase not? Because, you know, when I measure the phase strictly depends on where I put the origin of my axis. And so if the goal is to get the phase at this point, you know, shifting the origin in forward by t half is not measuring, because now I measure the phase at the center. And on the contrary, I want to have the phase at the beginning of the interval. So this kind of operation is something that I cannot do. Now, so all the interval, so this is not 0t, but it should be changed, and these should be changed. Okay, so I change for all. Tell me.
I didn't understand the last part you said about you cannot set the phase, do this procedure for the phase.
Oh, because, I mean, what is the phase? The phase of sinusoid is the value. Let's do this one. Let's look at the model. The model is A sine or cosine omega 0
initial condition
T Q plus P. Okay.
You're saying initial condition of the phase is important.
Yeah, but,
so
you know, the initial condition is the phase is the value of the signal at t equals 0. Okay. So the phase. So if I look at the phase, you know, and assume that this is 0, and the phase is this value. Okay. Now, if I shifted the interval to the center, and I put artificially, now let's change the color, artificially 0 here, and this becomes t half, and here becomes a minus t half, then, you know, the phase at the 0 is different from the previous one. Okay. Now, so if the goal is to estimate the phase, then I should clearly define what is the experiment, and if the experiment includes that the windowing, the time window, goes between 0 and capital T, then the phase is measured in 0. Here. On the other hand, if I'm interested to the frequency, and the phase is not relevant, which means that phase is nuisance, then I can freely choose where to put the origin. Because, I mean, if I put the origin here, the phase is different from the phase that I have here. Okay? Now, for this reason, you know, this is the reason for the sentence. Okay? So, let me summarize. Okay? So, if phi is important, then you need to keep the time interval 0 t. Okay? If phi phase is nuisance, then you know I can freely select t equals 0 to be convenient. Okay, to be convenient for analysis, computation, and so forth. Okay, that's the point. So, you know, this is the case. I mean, so in this case, you know, the phase was not relevant, and so it was nuisance, and then I decided to integrate between the interval minus t half and t half. So revisiting, so that means all the like the the Fisher A. Okay, then you know it's computed by integral between minus t half and t half, and then for all the other amplitude of phase, and so forth. Okay, then I repeat for all. Now, when I do for this way, then you know, doing this way, then what I get is I don't have it. You know, let me compute it. Now. Here I computed all the Fisher information methods. Okay, so now consider this is the Fisher on amplitude. So 0 to t, rather than having 0 to t, I have a minus t half and t half. The result is the same. Okay, so let's use the blue in this case. So I have minus t half, t half. The result is the same. The integral is the same. Now let's consider the second case. Second case, you know, I have this integral, but it doesn't matter what is the extreme. It's always 0 for the reason we said yesterday. If I take amplitude and phase, blah, 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 for the same reason, the integral is 0. If I consider omega, okay, then you know, look at here, then I have a sine square. Sine square, you know, you only keep a 1/2. So it is a squared divided by n0, and then the integral. Now, the integral, if I take the integral between minus t half and t half, then this integral should be computed as a squared divided by n0, and then it is t cubic divided by 3, evaluated for minus t half and t half, which is, you know, is 2 times a squared divided by n0 divided by 3 n0, and then it is t cubic divided by 2 to the power 3. Now, okay, which makes 2, so it's 4. So that one is a squared t cubic. It is n0 multiplied by 12. So, you know, looking at the Fisher element in this case, so there is a smaller factor by 12. So this is the blue one. The blue means integral between minus t half and t half. So I'm repeating. I might ask you in the exam, I might ask, repeat the same computation for the case where the interval is symmetric, okay? So you take the already done and you simply, change what is necessary. Now, similarly here, now this is the Fisher information matrix for omega and phase. Blah, 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 blah. But look at here. This analysis for integral between, let me write it, 0 and t. But if I apply in blue between minus t half and t half, then this becomes different. This becomes 0. Because when I integrate the t between a symmetric interval, the result is 0. Further, I have a sine square. Okay. Now, this sine square is 1/2 plus a cosine. Okay. And then, so let me make it here. This one is 2 times a squared divided by n0, and then it is integral between minus t half and t half of 1/2, because the other is 0. Is a cosine, is an integral of cosine, which is 0, and dt. So this is equal to, so this goes away, so it is a squared divided by n0, so it is integrated between t half and minus t half, so it's t again, which means it's not changed. Okay? So the new Fisher information matrix that let me collect all the Fisher, the blue one. So the Fisher information matrix in this case becomes t0 divided by n0, so 1/n0 is collected, t0, 0. Then this one is 0, this is 0. Now, here goes the frequency, and the frequency is a squared t cubic divided by 12. And then the third position is a squared multiplied by 2. So, in case, okay? So what I can say is that the variance on the frequency estimation, in case I'm decoupling the parameters, is equal to, the inverse for that, so is equal to n0 2l divided by a squared t cubic. Now, so comparing by the computation made by using the full matrix, which is carried out here, we can say that they are both the same. So, since they are the same, we can conclude that taking a symmetric interval or not is not changing the corresponding camera. Okay. So it depends, the variance depends on the inverse of the time to the cubic. So the bigger is the interval, so the variance is decreasing with the cubic of the observation window in time. Now, you know, I see here, but you know, let me make it. Now, everything we said is for continuous time. Now, can I take this continuous time and map onto the discrete time such that the results that I'm making with the discrete time makes sense? So can I use the continuous time parallel to get the discrete time parallel? Now the answer is yes. How can I do it? Now, so I know that the variance of omega 0 is larger or equal than n0 2L n0 divided by a squared t cubic. Okay, this is what I know. Now, you know, usually it's better to describe the variance or the Kramer bound with respect to, considering the ratio between, you know, the power of the signal and the power spectral density of the noise. So it's more convenient to rewrite this one as n0 divided by 2. Okay? And then I have a squared divided by 2, which is the same, time 2L divided by t cubic. So, you know, this is equal to 12 divided by t cubic time 1 over signal to noise ratio, where the signal to noise ratio is the power of the signal and the power spectral density of noise. These are collected into the exponent. Okay, so sometimes, you know, it's more convenient to write in this way. Now, I want to make it. I told you I want to make it to reconsider the discrete time case. So how do I make the discrete time? So that means now that my model is a sample. Okay, and the power spectral density, which is constant, n0 divided by 2. This is the power spectral density, okay, for the continuous time. For the discrete time, what I need to do is to pre-filter. So, you know, I should assume that there is a filtering of the power spectral density within the certain time bandwidth interval. So let's assume that, you know, I'm sampling at a certain frequency, which is 1 over delta t. If I'm sampling at this time at a certain frequency, then, you know, the time in window t is equal to n samples multiplied by delta t. Okay? Because, you know, this is the time window in samples. Okay? So, in other words, it means that n is equal to t divided by delta t. Good. Now you know. What is omega? So omega 0, okay, which is in hertz. So if I look at, you know, I have cosine omega 0 t plus phase. But you know, if I'm sampling here to delta t, this is delta t multiplied by n. So this omega 0 times delta t is called normalized frequency. Angular. Okay? So this omega tilde 0 is limited to pi for sampling theorem. Okay? For sampling theorem. So, you know, what I can say is the following, is that, if I'm computing now the variance on delta t, okay, so the variance of omega 0, then omega 0 here is equal to omega 0 tilde divided by delta t. Okay? Now, let's put all the pieces together. There is still one piece which is missing. If I sample the signal, I cannot sample any signal, specifically any random process, if I'm not pre-filtering. Which means, if I'm filtering the noise, a random process that is spectrally white, okay, I need to be sure that the bandwidth is limited. So I can assume that the bandwidth here is limited to 1/2 of the sampling frequency. So that means that here I have a minus 1 to time delta t and 1 to 2 time delta t. So in case I'm filtering the bandwidth, the power of the noise is given by this area. So the power of the discrete time noise is equal to sigma squared w, which is given by the variance, and it is equal to n0 divided by 2 multiplied by 1 over delta t. That's the power, okay? Which is similar to the proof that we did for evaluating the maximum likelihood for continuous case, okay? That's exactly the same. Now we take all these pieces and we put together, okay? Now, what does it mean, the variance of omega 0? So the variance of omega 0 means that it's equivalent to the variance of omega 0 tilde divided by delta t squared. Because since, omega 0 is omega 0 tilde divided by delta t, then variance of omega 0 is variance of omega 0 tilde divided by delta t squared. Delta t squared, which is the sampling interval. Okay, let's put all these together. So I have variance of omega 0 is equal to the variance of omega 0 tilde, which is what I'm looking for, my term of interest, divided by delta t squared, which is equal to 12. I'm copying, copying that one. 12 divided by t cubic. But what is t cubic? It's n times delta t. Okay? So, let's use it. So it is 12 divided by n t cubic, which is n cubic delta t cubic. Okay. That's that one, or that. Now we have n0 divided by 2, a squared divided by 2. Now a squared divided by 2 remains the same. And in the numerator, I have n0 divided by 2. Now what is n0 divided by 2? Looking here, is a sigma squared w. So, using this relationship, so let me put a number to each. So this one is sigma squared multiplied by delta t. Then all is finished because I have all. So the variance of omega 0 tilde, which is for the discrete case, is equal to 12 divided by n cubic Then I have a time, delta t squared divided by delta t cubic multiplied by sigma squared w times delta t divided by a squared divided by 2. So this goes away. And then this is equal to 12. So it's 24 if we want, it depends on how you want to put it. So this is 12 divided by m cubic, then multiplied by 1 over a squared divided by 2 divided by sigma squared w, which is the SNR. So this one is the discrete time value of the parameter bound obtained by the continuous time parameter bound. So sometimes you don't know which one is easier to get, and then my suggestion is, explore if it is easier to make a sum, like the discrete time parameter, or if it is easy to make an integral as a continuous time parameter. Now, since when you reread everything, in order to help you to see which equality I used, so for this one, the first equality is number 1. I used here, number 1. Now, for the second equality, number 2, I use this one. Okay, that the length depends on the number of samples. What else? Oh, for this one, which is number 3, I used this one, which is number 3. So aggregating everything together, this is what I got. And looking back to the Kramer bound for sinusoid, which I think is somewhere here. No, where is it? I probably can get it. Do you have a formula for the Kramer bound we derived? Which one was that? I think it was 8. No. Do you remember where we derived the Kramer? So it should be coincident. I don't have the book, so if you have the book, you can check the formula. You have the book, right? Can you look for
Where is
the formula for variance of frequency of a sinusoid in a discrete case? Should be this. Anyway, we will see that. Okay. Check. By the way, you need to check in the book for the case where the number of samples is very big. So n going to infinity. Huh?
It's 6 multiplied sigma power 2.
6 times
Sigma power 2 w multiplied divided a power 2
divided by
a power 2
a power 2
multiplied n power 2
n power 2
power
should
3.
power
It's the base of 132.
3. Okay. 32. Okay, so which is the same. Okay. So we derive it in another way. Now, just to tell you that the continuous time and the discrete time, there are two two sides of the same coin. Okay. This means that sometimes you need to derive the property in a continuous time, and then you apply to the discrete time, because when you process your signals, you process as discrete time signal. Now, okay, this one was, a longer one to look at the estimation of the sinusoid. Now, a new exercise. The new exercise here, so let's change the subject apparently, but for me they are very similar, okay? So this one is from this exercise comes from the first intermediate in 2016, so which means 2 years ago, the same situation where you are Monday, okay? So let's read it together. Now, first, derive with a clear definition of the assumption that the maximum likelihood for a continuous time signal in additive white noise model. Okay, look. Let me say, this is the theoretical side, okay? Which means, if you study, you can answer that. Now, let's go. Consider the signal for the time of delay estimation, and the data within the observation interval, which is 2 milliseconds, is the following. So I have this echo, which is an echo, okay, is AGT minus tau plus W. So what I'm measuring, if you like, I'm measuring something, and the pulse is almost, the rise, the cosine. This is tau delay, and the amplitude is A. Okay. So this is the signal I measure. So this is what I sketch in this XT. Now, where the waveform, okay, G of t is 1 plus cosine 2 pi 1 megahertz times t, up to half a millisecond, and is 0 elsewhere. And W is a white Gaussian noise with power spectral density and 0 divided by 2. Okay, so first of all, draw the waveform G of t, placing attention to the units. Now, I already copied from from the solution of the exercise, okay? Because I don't want to waste too much time. So it's a cosine. So this 1 plus is taking cosine and moving up, okay? So it's shifting up, and then it's going between minus half a microsecond to half a microsecond. So this is the pulse. So the pulse, so the duration of the pulse at Tg is equal to 1 microsecond. Okay, so I have a pulse of 1 microsecond resolution. Placing attention to the units, so which means, 2 is the amplitude, 2 microsecond is the interval, so place attention to the unit means put the number, okay, which is necessary. Now, first of all, first question, okay, so draw that, okay, is given there. Now, second, compute the energy of the waveform. So compute the energy means compute the energy for that. Okay? So the energy, what is the energy? Since the waveform is already given, which is this one, so what I do is I compute the energy. And I also copy this. Okay? So the energy of the waveform is, since the waveform is 1 plus cosine, here, to the square. Okay? So the energy, since the energy is equal to the integral of g of t squared dt, and the integral can go between minus infinity to plus infinity. But since the pulse is limited, is in length, so it doesn't matter what is the integration interval. Now, when I compute the energy itself, then it is 1 plus cosine squared between the interval Tg. Then it is 1 square is 1, cosine square is cos square, and then it is 2 times cosine. Okay? Now, so this one is 1 plus cos square plus 2 times cos. Okay? So 2 times cos, you know, is 0 the integral. Okay? Because it's the same waveform, except it's shifted up. Okay? So the integral for this one is 0. So the integral of 1 between the interval tg is equal to tg, and the integral of cosine square within 1 period is the you know, it's equal to the period divided by 2. So that is a very quick way to get to the energy. So when I sum all, the energy is equal to 3, so it's 1.5 Tg. So the energy is equal to 3 Tg divided by 2. Now, this is the easy part, okay? So let's continue reading. Define the maximum likelihood function for this problem with the parameters amplitude and delay. Okay, so amplitude and delay are the parameters of the problem. Derive the maximum likelihood estimator, the maximum likelihood estimate for amplitude with known tau. We solve it, okay, because this one is the cross correlation calculated in tau zero. Okay, so we did it. I mean, not last week, but you know, sorry, not this week, but last week. So done. See past exercise. Derive the maximum likelihood method for tau with known amplitude. Cross correlation again. The same as the previous one. In the previous one, you know, I fixed the delay, and the second case, you know, I fixed the amplitude and I leave the delay as a free parameter. Then also this one. Now, optional. Okay, optional. Delineate an application field that might apply this signal model. Radar. Sonar. Geophysical signal. You know, anything that has to do with a delay. Okay. Finding the size of the room, tracking hand, and finding the echo. Okay, and so on. Optional is optional. Okay. Optional means if you make it, I value positive. Okay. But you know, the total is fixed. So if you do everything perfect, then you know, I give you the maximum plus. Okay, for me means, you know, you are a little bit better. Okay? Compute quantitatively the Kramerau bound on the time of delay. Okay, now the question is one line, but now you know it's more takes more time. Now let me read all. Evaluate numerically the minimum signal to noise ratio to guarantee that the time of delay is estimated with an accuracy at least of 1/10 of microsecond with the probability 99%. Okay, so that means that, you know, in this case, okay, I want that the time of delay that I estimate should be accurate. So the variance of the time of delay should be, so the variance, the effective value, okay, so the square root of the variance should be smaller than 1/10 of the microsecond. Okay, so you know, I define the degree of accuracy. And the option. So you know what you notice is it's getting tough and tough. Okay, it's getting more difficult and more difficult. So I would say, you know, I mean, the easy part is up to there. Okay, just to give you a self-evaluation for you. So you know, if you do up to here, you probably bring back. So you make half of the exercise, a little bit off. Okay, so that you have an idea. Huh? So from here to there, probably you get approximately 40% of the exercise. Okay, this makes 60%, which means it's the most complicated part. Okay, now let's make it. So I need to compute, you know, the quantitatively the Kramer-All bound. Okay, now we know that to get the Kramer-All bound, this is a continuous time. So in order to get the Kramer-All bound for this experiment, okay, I need to calculate the Fisher information matrix entry. So, you know, let's with a little bit of patience, we make it. Okay. Now let me copy the waveform because it's important. So to get to the Fisher information matrix, okay, now I need to get amplitude, I, amplitude, delay, I, delay, amplitude, I, delay, okay. So what do I need to compute? So I need to compute, you know, the gradient of the derivative of amplitude g of t minus tau with respect to amplitude. And this is equal to g of t minus tau. Then I need to compute the derivative of a g t minus tau with respect to the delay. And this is equal to minus a g prime t minus tau. Okay. Now, I know that I amplitude tau is 0. In case I don't remember, you know, I can say that I can calculate. So this is equal to, so it's a combination of these two terms. So it is integral of derivative with respect to a of s times the derivative with respect to tau of s, the sigma dt, which is, you know, it's 2 times n0, it's minus a times g t minus tau, g prime t minus tau dt. So, you know, now, if a g is odd, g prime is even. Okay. If a g is odd and even, g prime is even and odd. So at the end of the story, this is equal to 0. So the integral, not these terms. Okay. So, you know, overall, this means that this is equal to 0, this is equal to 0, and the problem is decoupled. If you remember, fine. If you don't remember, you need to, I expect you make this reason, okay? Then, what I need to calculate is the following. The Kramer-All bound, so the variance of tau n is larger or equal than the Kramer-All bound on the delay, which is equal to 1 over I tau tau. Okay. So let's calculate this I tau tau. Now this term I tau tau, which is the Fisher information matrix on the delay, is equal to a squared 2 times a squared divided by 0, and then it is integral of g prime t minus tau dt squared. Okay? Because, you know, I mean, I'm simply, I tau tau means that I'm taking this multiplied by itself. Okay, just So it's 2 times. So this multiplied by this, so it's a square. Okay? So that means that I need to calculate g prime, and I need to calculate the square of g prime. So what is g prime? You know, g prime is the derivative of that one. Okay? Is the derivative of that. So what is the derivative of a cosine? Sine, right? Okay. So I take this waveform here, which is defined in analytical sense, and then I calculate the derivative for that. Okay. So I go on the back. Let me go on the back. So I take this one and compute the derivative. So the derivative of the constant, 0, right? And then I have the derivative of cosine, which is minus sine. Okay? So remember, it's the derivative of with respect to time of the cosine. So it is sine of blah blah multiplied by 2 pi 1 megahertz to the square. Right? You follow me? Okay? So now let me just to simplify 1 megahertz or not. Okay, let me call this one omega 0 just to give a label. Okay. So then you know my derivative is, you know, if I don't want to compute a derivative by formula, I can compute a derivative by graphical. So you know here is going up. So the derivative is positive. Then here the derivative is 0. Here is 0, the derivative. Okay, so 0, 0, 0. So 0, 0, 0. And then you know the derivative is the sine. Okay. Now, if you want, you can compute analytical, or if you want, you can compute graphical. Okay, it's up to you, whatever you feel confident. So now you need to take this one, okay, to the square, because this one is g prime, because this one is g, and that is g prime, so it's the derivative of g. Now, I need to take this one to the square and integrate dt. Okay, graphically. I'm against analytics, so you know I'm for graphically. Okay, so now you know. I mean, this is a sine square. So you know this is sine square within a period, right? Sine square within the period. So I can calculate that because it's the period divided by 2, right? Okay? So you follow, who is not following, okay? So the square of a sine is a sine square. And what is the integral of a sine square? It is the period divided by 2, okay? If you don't like it, you know, consider that if I have a sine square, this is equal to 1/2 plus 1/2 cosine with the double frequency. But since the double frequency is going up and down, when I integrate this one, the number of positive lobes is equal to the number of negative lobes. So that goes away, okay? Whatever, do as you like. You know, the engineering way is the number of positive is equal to the number of negative, close. This goes away, okay? If you are analytics, do as you prefer. So let me finish that. So you know g prime. Now the amplitude for that one, okay, is the argument, which is omega 0. The amplitude of g prime is omega 0, okay, because I have a cosine of omega 0 t, and when I calculate the derivative, this is equal to omega 0 sine of omega 0. Okay? Fine? sorry, minus, but it's a square, so it doesn't change, okay? Is it clear? So when you make it a square, it's a square of omega 0, okay? So let me continue. So let me copy. So I have I tau tau, which is equal to 2a squared divided by n0. Then I have the integral of g prime t dt squared. But you know, this is equal to the amplitude, so it is 2 times a0, then it is time omega 0 square, because it's a square, right? Then it is n0, and then, you know, it's the period divided by 2 time the period of the waveform, huh? So it's tg divided by 2. Okay? Where, you know, omega 0 g prime is equal to omega 0 minus sine omega 0 t. Okay? So you recall. Okay? So, you know that. Then I have everything. Okay? This goes away with that. Omega 0 I remember. So Tg was, how long was Tg? 1 microsecond. And omega 0 was 1 megahertz, which is the inverse of 1 microsecond. So it's 2 pi divided by 1 microsecond. I prefer to put everything in 1 microsecond. Okay. So I tau tau is equal to a squared n0. Then I have 4 pi square. Then I have 1 microsecond square multiplied by 1 microsecond. It's 1 microsecond. This is I tau tau. So the variance on tau hat is the inverse. Which is equal to 1 microsecond divided by 4 pi squared multiplied by 1 over a squared divided by n0. That's the result. Okay. So there is one parameter in the exercise which is totally irrelevant. If I go to see the text, in the text I see one parameter. I remember now. I see one parameter. The data within the observation interval 2 milliseconds. But you know, t equal 2 milliseconds is not used in our solution. It's not relevant. It is only saying that 2 milliseconds is bigger than 1 microsecond. 2 milliseconds, 1 microsecond, okay? Evaluate the mean, okay? Now I can check with my, you know, because I took it here on the last year. I represented, I did slightly different here. I represented everything with respect to Tg. So, you know, I calculate everything with respect to Tg. So, let's do it. So, how much is the energy? The energy is 2 times Tg, 3 times Tg divided by 2. Let me get the result. So, what is the energy? The energy of G is 3 times 2 divided by 2 Tg. So, I can, you know, I can recalculate everything with respect to that. So I can multiply and divide by Tg. This one is the TG. TG is the duration of the waveform. So I can write it this way. This is TG squared divided by 4 times pi squared. And then I divide by 1 over TG. Multiply the divide by TG. Now, if I multiply 3 half and divide by 3 half, then I'm not doing anything. Now, multiply by a squared divided by n0. So a very convenient way to represent is this. This is the energy of the waveform. So this is equal to Tg squared multiply by 3 divide by 4 8 pi squared times 1 over energy of the waveform a squared divided by n0. Usually, this term is called the CO2 noise ratio. So the variance depends on the square of the TG scaled by 3 divided by some numbers. So the variance depends on TG. Now, so if that one is the synchronous ratio, now assume that, as in the question, assume that I want that the variance of tau, F, which is larger or equal than the Kramer-Hall bound, and the Kramer-Hall bound depends on Tg squared, then there is a scaling factor, then there is a synchronous ratio. Okay. So the text is asking, what is the synchronous ratio to guarantee that this one is at least some number? Now, what was the resolution? The text says that I want that with a probability of 99%. Now, what does it mean 99%? So if my, if I make my estimate, and the estimate is distributed Gaussian with respect to the true parameter, my uncertainty should be limited within the interval of plus minus 1/10 of microsecond with the probability, when I say probability I make an area, with the probability of 99%. So with the probability of 99%, any estimate should be within within a deviation of at most 1/10 of microsecond. So how do I solve it? Now let's solve this one and put into from the natural words, let's put into the mathematical way. So what I'm saying is the following. What I want is that this Kramer-Hall bound, okay, should be, this one is the minimum, okay? So if it is fulfilled for this, it's fulfilled for everything, okay? So I want that this one is smaller or equal than 1/10 with a probability of 99%. So what does it mean 99%? 99% means that if this one is a certain sigma with respect to the time of delay, sigma tau, then I need to have that 3 times sigma tau should be smaller than 1/10 of microsecond. How much is this sigma tau? That's it. Now I repeat here, okay? Now the text is telling you, that any estimate tau hat, okay, is distributed you know, as a Gaussian distribution, which is sigma tau. Sigma tau is a standard deviation. So since any estimate is distributed like that, I know that the variance of tau hat, which coincide, which is that one, sigma tau. Okay? This variance is, you know, is lower limited by the Kramer-Rao bound on tau. This is one statement. But you know, the text is telling me that, you know, I want that every estimate, so every estimate should be contained within a certain interval. And the interval is plus minus 1/10 of a microsecond with a probability 99% of probability. Okay, so which means that plus or minus 3 times sigma tau, which is 3 times the standard deviation, which is approximately 99% of probability, 99.9 probably is going to be. So plus minus 3 times sigma tau, okay, should be equal to 1/10 of microsecond, plus minus 1/10 of microsecond. This is the statement. So sigma tau should be, you know, that's the maximum. So sigma tau should be smaller than this one, because that's the worst case. So sigma tau should be smaller or equal than 1/30 microsecond. Okay. Now I take 10.
From where do you get the value of 1/10 microsecond?
From the text. Evaluate numerically the minimum signal-to-noise ratio. That guarantees that the time of delay is estimated with an accuracy at least 1/10 of a microsecond, what at least, which means smaller, okay? With the probability 99%. Yeah. So I want that, you know, this is the deviation, 1/30 microsecond, okay? So this means that sigma square tau should be smaller or equal than 1/30 square microsecond. So going back to our formula, it is essentially, now I take that one here. So I say Tg squared 3 divided by 8 pi squared. This is a signal-to-noise ratio, okay? This one should be smaller than 1/30 microsecond. So Tg squared, copy, 3 times Tg squared divided by 8 pi squared time 1/signal-to-noise ratio should be smaller than 1/30 squared microsecond. But since the Tg was 1 microsecond, so
When you run the variance, shouldn't be also the microsecond squared, so also the unity measure?
right, this one as well. Okay. So since you know now Tg was 1 microsecond, let me check. Yeah, Tg was 1 microsecond, okay? So putting this 1 microsecond inside here, which makes 1 microsecond squared, okay? But you know what I'm saying is, here I have a microsecond, on the other side I have a microsecond. So you know, they are compatible on the units, okay? If on one side you have a microsecond, on the other side you have a second, please put on the same units. Huh? Okay. I don't know, it's trivial. Okay. So this is saying that, I don't know, so this is 30, so I have a 3 times, so it's, I want to make it, so it's SNR is larger or equal than 3 times 8 to pi square. Then I have 1 microsecond square on the other side. I have 130 square microsecond square. So the units are the same, okay? So which means it's 3, 9, 900 times 3, 8 pi square. So whatever it comes, okay? So that means that the signal to noise ratio should be larger than blah blah. Okay. Let me see how much is that. Just don't be shy with the numbers. So now approximately pi is 3. So this pi square goes away with 9. This is 300, so it's 300 divided by 8. 37. Approximately, okay. So, 37 for our telecom people. Let's put our telecom and electronic. We put in logarithmic. So it's is 15.7 digit. Okay. For math, it's not necessary the degree scale, of course. Now, let's see what the text is asking again. It's not finished. Okay, say, it is known, the text says, it's optional. They say, it is known that the usage of M measurement with independent noise and the same parameters like that one can improve the MSC performance by 1 over N. Can you evaluate why and how, possibly by simple and intuitive reasoning rather than complex analytical computations? So, look at the answer is already given here. So, what I'm asking is the following. If I have a set of measurements, and these measurements are, they have the same parameters, which is the same amplitude, same delay, but different noise. Now, this kind of experiment is specifically as the radar happens. In a radar system, I'm telling for the non-telecom, okay, because telecom knows. So for a radar system, the transmitter is sending not just one pulse and receiving that pulse and making everything with that pulse, but is receiving many pulses. So the transmitter transmits many pulses, and and after, let me now that we understood all the trick. Okay, so now in a practical system, what's happened is that I have let's say my radar that is measuring that and is receiving. Okay, this is the target. I don't know. It's Germany. Okay. And so what's happened is that I'm repeating to transmit pulses. So what I get is a sequence of pulses. Possibly very noisy. Actually, no. Let me resketch. This is X1 of T. Since I'm synchronized, so every transmitter is synchronized, so every pulse is perfectly synchronized. So what I take I do this way, actually, no, technically it's done this way. So this is the signal. Okay, this is what I receive, okay? Since I know that the 0 is here, so I segment this time window t, and and I move one on the top of the other. So which means, I put this one here, the second here, the third here, and so on. So, I have a set of signals with a lot of noise. Usually this number of samples are very big. So I simulate an experiment as if I am repeatedly measuring the same target. And the reason why making that is because I improve the signal-to-noise ratio. Why am I doing it? I mean, what I'm asking is make it an intuitive way. I don't want many big formulas. Okay, so how can I do it intuitively? It's already in the formula. I mean, how can I get it? I do this way. So I have xm t using the formula is a gt minus tau. These are the tau, all there. Okay, gt minus tau plus wm t, where wm is different one another. Okay, so easy way to do that would be that I sum all that. Okay, I sum all that and I divide by m. So if I sum all that and divide by n, what I get? I get the compound signal, which is xt, which is obtained by summing m of xn, which is equal. Now, the term on the right here, on the left here, is the same. So I'm summing every time the same, divide by n is the same. So that is equal to a gt minus tau plus I have sum of w and t divided by n. Now I have a signal plus noise. Now this is a compound noise. Let me call this one as w tilde. So I can get the characteristic of this noise. And if I want to calculate the characteristic, for instance, I have the noise, and about the noise I can calculate the mean and the correlation. This is a continuous time, the correlation for that. So I use the definition. Now for correlation, so I use R, W tilde, tau. Tau is T. Okay. Now this one is by the definition, so it's W tilde. Alpha, W tilde alpha plus T. Integral in the alpha. Now, this is equal to sum over m of w m alpha time sum over n of w alpha plus t, the alpha. Now here, this one I have a divide by n, here I have divide by n. Okay, so this is equal to 1 over n squared. Then I have a sum of terms. Now, this is equal to the sum on n only, because n and n are uncorrelated. So is the sum of m of w n alpha w n alpha plus d alpha. So, you know, this one is the autocorrelation of the Gaussian process. So this one is n0 divided by 2 delta t. So it's n time this autocorrelation. And this is equal 1 over n squared time n0 divided by 2 delta t, which is equal to, essentially it's 1 over n time n0 divided by 2 delta t. So, you know, the noise is scaled by 1 over n. Okay, I forgot the expectation, okay. All contains the expectation, of course. So, you know, that is, I mean, an intuitive way. So, I mean, that means that the signal is persistent. The noise is varying, averaging the noise, you know, the variance of the noise, or if you like, the power spectral density, or if you like, the autocorrelation is scaled by 1 over n. That's the conclusion. Now, let's make another. Okay, so now this was, I read it and we make 5 minutes, no, I read it and then we solve it together. Now, let's read. Derive a blah 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 saying, book. Derive a clear definition and assumption of the maximum likelihood for continuous time signal in additive white noise model. Okay? Now, second. Consider the signal in an acoustic sensing system, okay, where distances of a backscattering target are obtained by their time of delay estimation. I make this way, I get an echo, and from the echo I can estimate the position, like the bat, you know. The bat are not exactly transmitting this. I think I told you, the bat are transmitting chirps. And you know, and they're transmitting chirps such that for the bat, it's easy for the bat to transmit orthogonal chirps. Otherwise, every bat doesn't know if the transmitted pulse was transmitted from another bat. And so they collide. You know the bat, small flying animals, okay? They are totally, you know, you can touch it. You can touch these animals. They are not killing you. So the women usually don't like because they say that the bat goes to the hair. It's totally false. Okay? So, you were saying something.
So the bats, each of their sound is orthogonal to each?
Yeah, because every bat
because
is transmitting the chirp.
Yeah.
So they transmit like very easily. So they make, so they transmit this like, now I extend, okay?
Mm-hmm.
So they transmit like, okay?
Mm-hmm.
And so, you know, they can make it orthogonal this way. Because if you transmit like a click, then you don't know exactly, I mean, which click is the one that you receive as an echo. So you need to make it orthogonal, right? Anyway, so, and my wife is caring about the bat. Okay? So one day, enter the bat into our house, it was like if, you know, devil entered. It's that big, you know, even that. And the poor animal was totally scared. So, I mean, I closed the door and I took the poor animal. Anyway, so consider this one, okay? So the acoustic system. You know? The data is within the observation interval of 200 milliseconds. Now, the signal is A, G, T minus tau plus WT, where the waveform GT is illustrated in the figure with TG equal 1 microsecond, okay? So 1 microsecond, you know, it's 1 gig, is 1 megahertz. So it's very high frequency. You know? WT is a white noise with power spectral density and 0 divided by 2. Okay, sketch a possible experiment for that. Now we make it. Okay, we continue on that until we are on the hot topic. Yeah? Okay, compute the energy of the waveform. Now, how to compute the energy? You know, learn how to make it quick. How would you compute the energy here? Now, I mean, one analytically correct way, but time consuming, is to make this integer, so the energy is the integral of the square for that. Right? That's the energy, okay? Am I right? No? No. You know, can I do easier? Because I mean, this implies, look to me, this implies that, you know, you need to write 4 equations. 3 equations. 1 equation here, 2nd equation there, and the 3rd equation here. Because I don't give you the equation of the line. You need to write the equation of the line. Am I right? Okay. So, you know, now, rather than make an integral here, you can look at that for the integral purpose, only for the integral purpose, this integral is equivalent to 4 times the integral of the square of this waveform. Okay? Because, you know, I mean, this one is symmetric of that. This is the same as that when you calculate the square. This is the same as that when you calculate the square. Because you need to calculate the area, right? Okay, so that is more easy. It's easy because, I mean, to calculate that one, it's here it goes from 1 with a slope that is Tg divided by 4. And so the equation of a line is, so here is simply compute the integral between 0 and Tg divided by 4 of a formula that can be written as T divided by Tg divided by 4 to the square. So I have T square, and you know, it's integral of T square, which is T cubic divided by 4. Okay? Simple, no? Okay. So, compute the waveform, the energy, fine. You know, define the Laplace function for that. It's the same as before. So the Kramer-Album is only left, and we continue after the break.